Hello and welcome back to the discussion sessions. Let me remind you in brief that last time we have, in our last discussion, we have discussed in details the structures that are used in machine tool dynamometer. These structures are cylindrical type, then we had the cantilever beam, the ring type structure, octagon and so on. And then I have shown it to you that what kind of machine tool dynamometer actual structure is used. Let us say in case of turning we have we can use the cantilever beam type structure, and by measuring the moment we can find out the force magnitude, because the distance between the force point of application of the force and the sensor, that will be known. Then there is a formula, of course, from the solid mechanics. We have said that from that formula we can find out the strain, and by measuring the strain we can indirectly find out what is the force, magnitude of force. Okay. So, once again I would like to tell you that in case of turning particularly, the forces which are measured, which can be measured at the Fc and the Ft, okay, normally, or rather you can say that it is Fc, Ff and Fr. So, this is in the three directions, that is 3 axes x, y and z. Okay. If you remember, I showed you those forces in turning. So, those were Ff in the feed direction, Fr in the radial direction and Fz in the vertical direction. So, these are exactly in three distinct axes. So, in the dynamometers, which are the modern dynamometers, those are the piezoelectric based dynamometers, they have the 3 axes, okay. Fx, Fy and Fz, these are the 3 components of the forces along the 3 axes, and they are supposed to be the Fc, Ff and Fr. So, from the Fc and Ff and Fr, you can find out the thrust force. So, that is why we say that basically we can measure 2 forces, which is thrust force and the cutting force, Ft and the Fc. Okay. Then we said, if you see here, that the ring type dynamometers are modified into the structure like this for the drilling dynamometer, and similarly the octagon structures are extended to be used in case of the milling or in case of the grinding. All right. And of course, I have shown it to you some requirement, that they should be sensitive, they should be rigid, they should have a linearity, they should have the good interaction, and they should be stable. Okay. These are the dynamometer requirements that we said. All right. Okay. So, now if you see in the slides, we will discuss next topic, which will be tool wear and tool life. Okay. Now, let me say that modes of tool failure. First of all, the tools during the process can fail, it can have fracture failure. So, cutting force becomes excessive and or dynamic, leading to the brittle fracture of the tool. So, simply it fractures. Okay. Temperature failure, cutting temperature is too high for the tool material. So, they get thermally deformed, or the gradual wearing of the cutting tool. So, to give you example, let us say we had a sharp tool, all right, and because of the high forces which are acting, the part of the tool can be broken, okay, from here. So, this is broken. In that case, the tool will have this kind of a shape, okay, broken. So, this is the fracture failure, or the temperature failure. Because of the temperature failure, this sharp tool may have, this is the sharp tool that we have, it may actually be thermally deformed. Okay. Or gradual wearing of the tool. So, we have the sharp tool. So, that tool can be gradually wear, because here the chip is flowing along this rake face and the flank face is rubbing with the already machined surface. So, therefore, these are the kind of gradual wear that may happen. temperature failure, that is the thermal effect, and the high cutting forces, or there can be dynamic cutting forces. We mean to say that when the cutting force is fluctuating, okay, the cutting force changes. So, in that case either it can be fatigue failure or it can be the high, because of the high magnitude of forces, the tool is not able to withstand that force. Okay. Now, these are the modes of tool failure. This is how the tools can actually fail. Well, mechanisms of tool wear, we have particularly main three mechanisms. There are other mechanisms, other points as well, but basic mechanism of tool wear are the abrasion, adhesion and diffusion. Okay. Abrasion, if one of the surfaces contains very hard particles, then these during the process of sliding may dislodge material from other surfaces by ploughing action. Okay. Now, let me give you an example. Suppose you have a chalk, okay, which is sharp, which is absolutely sharp and flat at other end, and you write something on the board. So, you will see the chalk wears out because the board material has the harder particle than the chalk material, and those harder particles of the board will abrade the softer particles in the chalk. Okay. So, therefore, it is called the abrasion. This is the mechanism which is called the abrasion. All right. Second mechanism is adhesion. When bodies of similar nature are in contact, the asperities tend to get welded. Sliding causes fracture of these welded junctions and material is lost from both the surfaces. What exactly is said is that I have shown it to you that two surfaces may sit on each other like this on the asperities. Let us say I am not making into scale, in scale. So, this is one surface, all right, and this is another surface, and these surfaces, both surfaces have the asperities. Asperities are the undulations, these are the undulations. So, these undulations are on those and on the part 1, and these undulations are on the part 2. Okay. So, now when these because of their own weight they may be very heavy, or because of the normal force which is acting on them, all right, these junctions will try to get welded. Initially, of course, these junctions will have the elastic deformation, and when the force increases, then it will have the plastic deformation, and they are trying to get welded. So, now if these are moving with respect to each other, suppose it moves with respect to this, or they are moving opposite to each other like that, in that case these junctions actually they break. Okay, these welded junctions break. Now, the broken particles remain within that. All right. So, adhesion, particularly when they are breaking, the material will be lost here on this and on this part as well. So, this is called the adhesion mechanism. This mechanism is called the adhesion mechanism, that when the asperities get welded and during the movement of these two parts, when they are sliding on each other, those asperities get or those welded junctions get broken, okay, and the material will be lost from both the parts. So, that is the mechanism which is called the abrasion. Diffusion, atoms in a metallic crystal lattice always move from higher concentration to that of a lower concentration. The process is known as the diffusion. So, let us say this is the these are the two surfaces, okay. These are the two surfaces. Let us say this is workpiece, okay, and this is tool. They are in contact with each other, and tool is working on the workpiece. So, the tool will have the atomic density more than the workpiece, because material is different. Let us say in case of tool, this can be made of high speed steel or ceramics okay, or diamond even. So, the atoms located here, I mean atoms in the atomic structure of the tool will be more in density, and therefore, the atoms will try to penetrate from higher density to the lower density, and the tool wears out. Okay. So, this is the mechanism that the atoms, these are the atoms, migrate from the higher density to the lower density. This mechanism is called the diffusion. All right. Now, the diffusion you might be knowing from the physics or from your class 10, 11 courses. The diffusion actually is facilitated by the temperature. Okay. More the temperature, more will be the diffusion. All right. So, therefore, during the machining process, as the temperature goes up, this actually facilitate the diffusion process as well. Now, what we have said about the three mechanisms, although the mechanism can be I mean for the wearing action, more than one mechanism can be responsible. We cannot say that this is the wear which is because of the abrasion only or because of the adhesion only. Let me give you an example. Suppose in case of these asperities welded junctions, when they are broken, we said that this mechanism is and the material is lost from both the surfaces, we said that this is the mechanism which is adhesion. But see, this wearing action that is taking place after these hard particles are sheared off, these particles will remain here, isn't it, within in the mating surface. So, these hard particles, they are also very hard because they are strain hardened material, because they are welded junctions. So, those particles, small particles, they will also have the wearing action of both the surfaces. So, those particles will also wear the softer particles, because those particles are harder once again. So, therefore, that mechanism is the abrasion mechanism. So, in that case we will say that if adhesion happens, the abrasion also can happen along with that. So, they can go parallelly, okay, or diffusion and one of them can happen also. So, normally what happens is that abrasion and adhesion they may happen together or separately, but diffusion is something else, because diffusion happens at a higher temperature. Okay. So, therefore, normally what happens is that when we machine, during the machining the temperature goes up, all right, but more temperature will be for high speed machining, all right. So, therefore, when the machining speed is very high, normally it is the diffusion wear which is responsible, and when the cutting process or cutting speed is not very high, it is low to medium, then normally the abrasion and the adhesion mechanism, they are responsible for the wear normally, all right. So, you must have heard about hard turning these days. Hard turning is a turning which is a high speed turning, where the cutting speed is very high. So, during the hard turning the temperature goes very high. So, in that case we can expect that the diffusion wear is predominant, it is more. Okay. Now, the progressive wear of a cutting tool occurs on the flank face, as I said here earlier, that this is the flank face of the tool, and flank face wears out progressively, because flank face rubs against the already machined surface, okay, in the form of a wear land. So, this is the type. So, this is the wear land, okay, that is formed due to rubbing against the newly machined surface known as the flank wear. So, this is the flank wear which happens at the flank face of the tool, because the flank face rubs against the already machined surface or newly machined surface, all right. As a result of chip flowing over the rake face, I just now told you here, if you remember, okay, in this case which is the gradual wear. So, because of the chip flowing along the rake face of the tool, this is the rake face, because this is the rake angle, and this is the flank angle. Okay. This is the machined surface, newly machined surface, newly machined surface. Okay. Let us say this. So, with this the flank face will make a flank angle. So, similarly it is said that as a result of chi flowing over the rake face, and this is the rake face of the tool, wear also takes place on the rake surface in the form of a crater. So, this crater is known as the crater wear. So, crater is like this. Okay. So, on the rake face a crater is formed. This is let us say the rake face, this is the tool, and this is the rake face of the tool. Okay. Flank wear is measured by means of a measuring microscope. So, flank wear is a land, okay, wear land. So, therefore, in microscope you can enlarge it and you can find out what is the value. So, it is measured in millimeter, normally it is measured in millimeter, because this is the land and what is the width of the land, that is what we are bothered about, or the length of the width, length of the wear land. Okay. So, normally it is the width of the wear land which is measured, and this is the measure of the flank wear normally. Crater wear, since it is a crater like this, okay, so this can be evaluated by means of a surface analyzer. You know the surface analyzer, it measures the surface roughness. Okay. So, there a stylus is there and stylus is moved along the surface. So, those asperities which are on the surface, those asperities will be sensed by the stylus, because the more if it is peak, so stylus will go up, if it is valley, stylus will come back, and this movement of the stylus is very sensitive and it will be measured by the amplified and measured in a device, and this can give you what will be the actually surface roughness, either in the in the micron. So, whether it is an RA or it is the RZ. So, these are the values, these are measured in the case of the surface roughness, and of course, the Brinell that is in the hardness. Those things we have discussed, by the way, in the during the discussion of our materials and properties. Okay. RA, RZ, what are those values? Those we will again discuss in the metrology once again in more details. Okay. Now, it can be evaluated by therefore the surface analyzer. So, if you put a surface analyzer on the surface, it will, the stylus itself says that what will be the crater depth. So, this depth here, this can be identified, this is the crater depth. Okay. This can be identified by the surface analyzer. Crater wear is formed at higher speeds when diffusion has been considered to play a major role. So, I already told you when we were discussing the diffusion, that in the diffusion, in case of diffusion, that atoms move, okay, from the higher concentration to the lower concentration, and since tool is the harder material than the workpiece, so the atoms are atoms are denser, that is that concentration of atom is more than in case of workpiece. So, therefore, the atoms will migrate from the tool to the workpiece at a sufficient temperature. So, temperature is a factor. So, therefore, we are saying that the crater, the responsible mechanism for the crater wear is the diffusion, whereas for the flank wear and crater for the flank wear, it is normally the abrasion or the adhesion, because flank wear takes place at a normal, at a lower or the normal speed, of course, at a higher speed as well, but at that time already the crater wear has been the flank wear has been formed. You understand that when suppose you are increasing the speed from the lower speed, at lower speed already the flank wear has been created, and because of the flat, the temperature further will be increased because of the machining, and the flank wear will be increased. So, that we will see after this. I was talking about exactly this, that this is the tool flank wear, and as the time progresses, time of cutting progresses, the tool flank wear, all right, progresses in this way. So, here it will have, this curve will have 3 distinct zones. One zone is this, which is called the break in period or initial break in also it is called. So, here it is a rapid initial wear. After that it will be actually very steady and the uniform wear. So, the wear rate will be uniform in this section, and this section is called the steady state wear region. After this, that will be a failure region, okay, and after sometimes it will be catastrophic failure. So, the tool will actually, tool can break, tool can be destroyed. Here it will be accelerating wear rate. So, it will be much more, it will be steeper than this curve, all right. Now, initial break in or the break in period is because the tool is sharp, as I said, that it may have the sharpness or it may have a little round of the nose radius, but as soon as the tool comes in contact with the workpiece, initially it gets worn out, particularly when the tool tip is sharp. Okay. Either it breaks or it gets a little radius during the, because of the rubbing, and the flank wear goes very high. Okay. So, therefore, this is the initial break in period, that is what we say, and then as the time progresses the wear goes very uniformly. Okay. It is not rapid and it goes uniformly as the cutting process goes on, but after some time the flat is still becoming more, the flank wear flat is still becoming more and more, although it is steady uniform, but it is becoming more uniformly. So, the temperature is becoming more and more because the flat is increasing, and then the tool wear also, this also gives rise to the further tool wear or the flank wear, and at a certain point this flat goes so high that the temperature becomes very high and the tool may fail any time after this. Oh, okay, and that is called the catastrophic failure. So, here somewhere in this region it is popularly known as catastrophic failure. Okay. In many books you will find that this is called the catastrophic failure, and here it is the uniform wear rate. So, the wear rate is very steady state wear rate. A tool that no longer performs the desired function, but it is not that it is unable to cut at all, is said to be reached the end of its usual life or it is failed. So, what we mean to say is that the to define the tool life, what is tool life is very difficult. Okay. Now, when we say that tool life has gone, then we say that tool life is over, we say that the tool is no more able to perform the desired level of the accuracy with the desired level of accuracy. Okay. The tool that no longer performs the desired function. Desired function is that particularly the dimensions and the surface roughness, all right, but it still can cut, but it will not be accurate, it will not be precise, is said to be reached the end of its usual life or failed. At this point the tool is resharpened and used again. Okay. And tool resharpening, you know that it is again taken out and it is resharpened in the grinding machine. So, that resharpening we will show you in the laboratory, by the way. We will show you the resharpening, how the resharpening can be done of the rake face of a tool, okay, in a tool grinder. All right. So, this is resharpened, tool is resharpened, but now what is that point which you will identify as when the tool is not working, all right. So, for this I mean to say that this is the region. Okay. In this region tool suppose may fail somewhere here or the tool may fail somewhere here, you never know that, you know. So, different tools may behave in a different way depending on the cutting process, depending on what kind of parameters you are using, cutting parameters you are using, and so on. So, in practice, therefore, tool life is taken in a different way. So, let us say here tool flank wear is taken in the y axis and time of cutting is taken in the x axis, like in case of this. Okay. So, then for different velocities, okay, at 100 meter per minute and 130 meter per minute and 160 meter per minute, if we conduct the experiments, then the curves will be like this, meaning that here this is a constant velocity and you are increasing the velocity in this way. You understand that for a certain process, when the process is going on, you cannot increase or decrease the speed. Okay, it is difficult. So, the process will continue, it will for sometimes you cut the material, okay, then you change the speed and then you cut the material again with the increased speed. So, that is what it has been done here for different speeds 100, 130 and 160. All right, the process has been carried over, let us say for along this, that is 40 to maybe 60 minutes, 1 hour, and these are the curves which have been obtained. So, as you understand from here, from the curves, from experimental results, that higher the velocities, rapid will be the flank wear, of course. Okay. More the speed, more will be the flank wear. That is one conclusion that you can get it. And then, as I was telling in this curve, that making sure that the tool has to be taken out for resharpening is very difficult, that at which point. So, normally what is done is that the flank wear, when it grows up to 0.3 millimeter, okay, 0.3 millimeter, then normally it is taken out. This is the let us say this is HF. HF is, what is HF is that if you take the tool like this, okay, this is the crater wear, this is the rake face, this is the flank face, okay, flank face, and this is the wear flat. So, this width, when it reaches 0.3 millimeter, then we say that the tool has to be taken out. Okay. This is the depth of the crater depth. So, once again this can be measured by the microscope, and as soon as it reaches 0.3 millimeter, so this tool is taken out for the resharpening. This is one thing. So, here of course, it is given 0.5 millimeter, it can be also 0.3 millimeter, let us say, as we said. So, we are saying that it is normally 0.3 millimeter. So, at 0.3 millimeter we are putting a line saying that we do not allow the tool flank wear to grow beyond 0.3 millimeter, because beyond 0.3 millimeter tool will not be functioning at a desired accuracy or the way that we want the tool to be function to give us the proper dimensional accuracy, proper tolerances, okay, and the proper surface finish. So, this is the line which will define the tool life. Then at this velocity at 100 meter per minute, this is the tool life. At the 130 meter per minute, this is the tool life, and at 160 meter per minute, this is the tool life. Okay. So, you can find out the tool lives at different speeds, and then if you put make the curve, okay, let us say we will put the cutting velocity here, all right. This is the curve that we will get, but here is the cutting speed here, we are putting, okay, and this is the tool life, So, this will be a straight line. Let us say we will put it in log Vc. So, this will be a straight line, and this straight line is represented by a formula which is Vt to the power n is constant, and this is called the Taylor's tool life equation, known popularly that you know. Okay. So, here the intersection of this with the velocity cutting speed axis, this is actually the c, okay, and the slope of the curve is the n. All right. Once again, this you take these values, these are the speeds, all right, 100, 160, 130, 160, and you take the tool life. So, here is the, you take the log of these values, okay, log of the speed, put it here, and log of these values of t, these values you put it along the y axis. Then it will be a curve like this, or the line like this, which can be represented as Vt to the power n is equal to constant, V is the cutting speed, cutting velocity, T is the tool life, N and C these are constants. N and C they actually depend on the tool and the work material combination. Okay. N is the slope of the plot, C is the intercept on the speed axis. So, therefore, we have to have the velocity here axis, and that intercept is the C, because you understand that here it is t is equal to 1, right, because we have taken as a log. So, log t is 0, and therefore, if we put the t is equal to 1, then V is equal to C. So, this will be the along the VC, this intercept is the C, that is the idea actually, and the slope here of this curve of this line will be will represent the n, this is the constant, C and n are constant. So, from this equation Vt to the power n is equal to C, which is the Taylor's tool life equation, what we can find out is that T to the power n, this is equal to C upon V, all right, and therefore, the tool life this is equal to C upon V, or C to the power n divided by V to the power n, all right. Now, here as we said that the C and n these are constants, and V is the cutting velocity, T is the tool life. Okay. N and C these are the parameters that depend on the feed, depth of cut, work material, tooling material, and the tool life criteria used. Okay. Now, here as you can see that the tool life has been shown by Taylor's equation, as we said it is dependent on the cutting velocity only, all right, because in this equation the T is equal to C to the power 1 by n by V to the power 1 by n. However, the variables like speed, feed and depth of cut, these are the cutting parameters, okay, they affect the material removal rate, as you understand this, and hence they have a direct effect on the production cost. You understand that if the speed is more, so the time taken is less, and more parts will be produced, same in case of feed and the depth of cut. So, therefore, the tool life has to consider these factors, because as you are increasing the speed, the tool life also decreases, because the tool wears out faster as you increase the speed. Similarly, as you increase the feed, for example, the load on the tool, so to say, will be increased, and so is the depth of cut. As you increase the depth of cut, then the tool wear will be also more. So, therefore, all these three factors, not only the speed that has been shown in Taylor's tool life equation, but also the feed and the depth of cut will also affect the tool life, all right. Considering this, the subsequent research after the Taylor's tool life equation has been invented, the research also says that the tool life equation can be expressed in the following way, that T is equal to this is the constant, let us say this constant is different than the C, C1 divided by V to the power 1 by n f to the power 1 by n 1 and d to the power 1 by n 2. So, these powers, that is n, n 1 and n 2, these have been found experimentally in the following way, that 1 by n is found to be more than 1 by n 1 and this is more than the 1 by n 2. Now, this finding, experimental finding, this indicates that the cutting speed has greatest effect, because this power of the cutting speed is more than the power of the feed than the power of the depth of cut. So, cutting speed has the greatest effect on tool life. This is followed by the feed and then the depth of cut. So, once again I would like to emphasize that this finding that 1 by n is more than 1 by n 1, more than 1 by n 2, these are the powers of V, F and D respectively. V is the cutting speed, F is the cutting feed and the D is the small d is the depth of cut. This is found out experimentally, and the conclusion that the V has the more effect on the tool life than the feed, followed by the feed and the depth of cut. This is experimental findings. Okay. Now, let us see next what are the variables that affect the tool life. So, basically there are 5 factors which will affect the tool life, that is cutting conditions, which we have already discussed, that is the cutting speed, feed and the depth of cut. Next variable is the tool geometry. In the tool geometry, we know that basically this is the tool angles, that is the 3 sets of angles, 1 set of rake angles, 1 set of flank angles and 1 set of cutting edge angles along with the tool nose radius. Okay. So, this all are included in the tool geometry. So, each one of them, that is the cutting each one of them is that the rake angle, flank angle and the cutting edge angle along with the nose radius, they affect the tool life. Okay, that we will discuss. Tool material, okay, depending on the tool material that is being used, the tool life will depend, or tool life will be affected by the choice of the tool material. This is very obvious. Going ahead, I should tell you that if the tool material is soft, the tool wear will be more if the workpiece is hard, for example. Okay. So, in that case the tool material has to be properly selected in case the work material is hard or work material is brittle. Okay. Next is the work material. Of course, this is related to this tool material. I just told you that if the work material is hard, then the tool material has to be cannot be soft, because in that case relatively soft. By the way, the tool material has to be always more, hardness of the tool material has to be always more than the hardness of the workpiece material. Then only the plastic deformation can be created in the workpiece material and the cheap, that is the excess material from the workpiece surface, can be segregated. That is one thing. So, when we say that tool material has to be soft, then we say that this is relatively soft, but it will always be more, hardness has to be more than the workpiece material hardness, of course. Finally, the cutting fluid. Okay. The cutting fluid, we all know that cutting fluid is necessary because the lot of heat is produced during the machining, all right. And I have already shown it to you. I will remind you once again that the temperature which is occurring during the machining, this depends on the Vc in this way, and the temperature versus the Vc, this curve actually goes in like this. So, this is the relationship, that the temperature varies with the cutting velocity by root over cutting velocity, and this says that at higher temperature, this is in degree, this is at higher temperature the higher cutting speed, the temperature will rise, all right. So, to take out most of the heat, of course, the heat is taken out by the chip also. Okay. Most of the heat is taken out by the chip. However, the remaining heat, this is conducted to the tool, because tool is in constant touch with the chip. Chip is flowing along the rake face of the tool, all right, provided of course it is the ductile material. In case of brittle material, as you understand that the chip breaks, and in that case the conduction of the heat to the tool will be relatively less, and a part of the heat will be flown to the workpiece. All right, those things we will see, we will discuss little later when we will discuss the thermal aspects of machining. So, therefore, overall if you see the cutting conditions, tool geometry, tool material, workpiece material and the cutting fluid, all these 5 factors affect the tool life. How they affect? Let us discuss it now. Now, effect of course, effect of cutting conditions we are not discussing separately, because here we have already shown that apart from the cutting velocity, the feed and the depth of cut also affect the tool life, and this is in this way that the speed has the greatest effect, followed by the feed and then the depth of cut. Well, how the tool geometry affect the tool life? Okay. Let us say first the rake angle. Now, we have already made very clear that increasing the rake angle reduces the cutting force and the cutting temperature, all right. That will result in the increased tool life, all right. So, what we are saying is that we increase the rake angle as far as possible, that is one thing, because increasing the rake angle ultimately increases the tool life by decreasing the cutting force and decreasing the temperature which is occurring during the machining process, that is one thing. And the reason I have already told you what is the physics behind it, that what happens to the shear plane as the rake angle is changed, shear plane is changing, and because of that as the rake angle is increasing, since the shear plane is decreasing, length of the shear plane is decreasing. So, it is the less effort in the cutting and the less force is applied, and as I said already, the less force applied means the cutting tool life will be increased, and also the the surface finish will be better, that is one thing. Now, again for large rake angle, the tool edge is weakened, resulting in the increased wear due to chipping of the cutting edge. So, what we mean to say is that this is the initial rake angle, all right, and if we are increasing the rake angle, let us say in this way, this will be alpha 1. So, alpha 1 is more than alpha. In that case, the cutting angle, which is this, is decreasing and the tool is becoming weaker. Okay. Tool is becoming weaker, it means that the tool edge is weakened, this the tool edge is weakened, and this will result in the increased tool wear, because it may break, it may chip in and so on of the cutting edge, because it is weak. It may even have the result in the mechanical breakage of the cutting edge. Okay. So, therefore, we cannot really infinitely increase the alpha, although the increase in the rake angle resulted overall in the increased tool life, okay. But to some extent, because at a larger rake angle again the tool life will be less. So, there should be some kind of understanding between the tool life and the rake angle, that how much rake angle we can afford to increase, so that the tool life could be at a desired level. Okay. Now, increased wear is also due to larger temperature, since the tool becomes thinner. As you can see, the tool is becoming thinner and the material available for the heat conduction from here will be less, material available is less. So, that we have already discussed earlier also once, that since the material available for the heat conduction is less. So, therefore, there will be more heat accumulation, and due to that there will be more thermal deformation of the tool, and the tool wear will be more, because tool will be softened, thermally softened, and the tool wear will be more. That is another thing. So, therefore, these are the two reasons. One is the tool is getting weakened, so it can actually break, and the tool wear can be more. Okay. Second reason is that the tool wear will be more because of the thermal softening of the tool, because it is getting thinner and less material is available for the heat conduction from this tool. Okay. Now, these conditions give an optimum rake angle, of course, as I said, which gives the maximum tool life. So, as I was telling that this is the compromise between the rake angle and the tool life, that we will increase the tool life till the increase the rake angle till the tool life is acceptable, okay, and we will not increase to that extent where the tool can actually break or the tool can be thermally deformed and softened. So, this is the condition that give an optimum rake angle which gives the maximum tool life. Higher is the strength of workpiece material, lower is the value of optimum rake angle. So, we have reached to an optimum level of the rake angle by adjusting the rake angle so that tool life is maximum, and this of the rake angle it actually lowers when the strength of the workpiece material is high, because hard material, to cut the hard material you need the fatter tool, you need to have the more material available for the heat conduction, because for hard material the level of the heat which is being produced, this will be more, and so on. So, therefore, higher is the strength of workpiece material, that means harder is the workpiece material, lower is the value of the optimum rake angle. So, optimum rake angle in that case has to be increased, because then the tool has to be fatter, tool has to have the more material for the heat conduction. Okay. These are the things which have been said here. Now, let us see the flank angle. Now, increasing the flank angle reduces the rubbing between the tool and the workpiece, and hence it improves the tool life. Once again I will remind that if this is the tool and here is the workpiece, this is the workpiece, this is the tool, all right. So, this is the flank face or the flank surface. Flank, or as I said that it is the clearance face also it is called, and this is the flank angle. Flank angle we designated by delta, all right. Now, if we increase the flank angle, again that rubbing will be less, because this flank face will be cleared and it will be safe, it will not anymore rub with the finished surface. So, this is the finished surface, finished workpiece surface, all right. So, again suppose we are increasing this flank angle like this, okay, and here the flank angle has been increased from delta to delta 1, where the delta 1 is more than delta, all right. In that case, again the same thing happening as in case of the rake angle that we have discussed just now, that the cutting angle which is this is less and the tool is becoming thinner, tool is becoming weaker, and the material available for the heat conduction will be again less. So, there will be again thermally tool will be thermally deformed, there will be thermal deformation of the tool. So, therefore, again there has to be a compromise and there has to be an optimum angle of the flank angle, so that the tool life could be maximum. After you achieve the tool life maximum with increase in the flank angle, after that if you increase the flank angle further, the tool life will be decreased. So, there is an optimum level of the flank angle as well, like in case of the rake angle. Well, however, too high a value of flank angle weakens the tool and reduces its life. That is what I discussed, that is what I told you here, explained it to you. Optimum value of flank angles is also affected by the feed rates. Okay. Higher is the feed rate, lower is the optimum value. Why? Because as the feed rate is increasing, we need to have more strength of the tool, because for higher feed rate the tool has to be stronger, because the more force will be exerted on that, because feed rate is more. Okay. The flank angle therefore, should be low if the higher feed values are used. So, this is an important suggestion that the flank angle which we have determined as the optimum flank angle for the maximum tool life, that has to be lowered in case the higher feed rate values are used. Okay. So, these are shown in the curves. So, first of all, once again I will come back to this, and this is as a reference point that tool life and the temperature in the log scale, this is in the T theta m to the power C 2. So, this is something that we have not discussed so far. This says that this is the curve between the log tool life in the log scale and the temperature. Okay. So, earlier in the tool life equation, Taylor's tool life equation, what we have seen is the log T, okay, and the no, this was log V, yeah, log V and the log T, and this was given as a straight line. Okay. Then we found out that it is not only the cutting velocity, but the feed and the depth of cut, they also affect the tool life. Okay. So, here it was V t to the power n is equal to constant. This is the Taylor's tool life equation, where only the velocity has been considered as the parameter affecting the tool life. Okay. Now, here this curve says that the effect on the tool life of the F and the D, or the feed, depth of cut and the velocity, can be combined in terms of the temperature. What it says is that as you are increasing the speed, as you are increasing the feed, or you are increasing the depth of cut, for all this combined effect is that the temperature is increasing. Okay. So, if we actually monitor the rise in the temperature, overall we can say that this is how the tool life is being affected because of the increase in all these three parameters: cutting velocity, feed and the depth of cuts. Therefore, this curve, that is the log T and the log theta, which is the temperature, okay, this says that there is a combined effect of the velocity, feed and the depth of cut in terms of temperature, and this is the line, or this is the curve in the log scale. This can be described by an equation T theta to the power m is equal to C 2. Of course, this C 2 is different than the constant that we have taken in the Taylor's tool life equation C, and this m is different from the n, that constant which you have taken in the tool life equation, Taylor's tool life equation. T is the tool life. Now, as we said, the in case of rake angle, what we said is that higher is the strength of workpiece material, lower is the value of optimum rake angle. First of all, we said that there is an optimum rake angle at which the tool life is maximum. So, here it is. Suppose you take any curve, any one of them, let us say, all right, let us say this curve. So, this is the curve describing how the rake angle varies with the tool life. So, initially as we are increasing the rake angle, the tool life increases, all right. Tool life increases because the cutting force decreases, surface finish becomes better, and of course, the temperature reduces, and the temperature reduces means the tool life is increasing. However, at this point when we achieve the maximum tool life, look at that point, this gives the maximum tool life. After this point, if we further increase the rake angle, the phenomena that I have already explained happens, that is the tool becomes weaker, less material is available for the heat conduction, and the tool life decreases. So, here if you see the right portion of this curve, that the tool life decreases. So, here is the optimum tool rake angle. Now, suppose if we increase the suppose this is the curve that has been taken for a particular strength of a material, particular strength. So, if the material is stronger, that is the let us say this is sigma 1, material of another material which is strength is sigma 2, and let us say sigma 2 is less than sigma 1 and sigma 3 even less than that. Okay. So, this curve is made for the machining with the same tool, but with different workpiece materials. This workpiece material is stronger, this is less strong, and this material is even less stronger than this and this. All right. So, therefore, we said that sigma 1 is more than the sigma 2 than the sigma 3. So, this is the strength of material. So, it is stronger material. So, in that case you can see this optimum value of the rake angle is lower in case of the hardest tool material, or the to more strength of the tool material of the workpiece material. If the strength of the workpiece material is less than this, in that case the optimum rake angle can be taken as a little more. Okay. In all these three cases we have a maximum tool life. Okay. So, keeping in mind that maximum tool life, we are determining what is that optimum rake angle. So, you can see that the for hardest workpiece material, as we have seen here, that higher is the strength of workpiece material, lower is the value of optimum rake angle. Exactly that is what it is demonstrated here, that this is the optimum rake angle for the hard, here it is said that high strength of workpiece material. So, the strength of workpiece material is hard is more, and the optimum rake angle is lower. Okay. Now, for the flank angle, we said that if the feed is more, okay, feed is more, in that case flank angle which is optimum has to be lower. Okay. I would like to show it here. Optimum value of flank angles is also affected by the feed rates. Higher is the feed rate, lower is the optimum value. Okay. So, higher is the feed rate, for example, in case of this curve, which is made with a feed rate of F1, which is more than the feed rate used here for this operation, and this is more than the feed rate that is used in this case. Okay. So, F1 is the maximum feed in comparison to F2 and the F3. All right. F2 is more than F3. In that case, as the feed rate is increasing in this way, feed rate is increasing order this way actually. Okay. That F1 is more than F2 is more than F3. So, when the feed rate is maximum, okay, comparing these three, then the optimum value of the flank angle will be minimum out of these three. Now, here if you take any one of these curves, what you can see here is that as the flank angle is increasing, the tool life increases, like in case of the rake angle. Okay. And the reason we said already that as the flank angle is increasing, then the rubbing between the flank face and flank face of the tool and the already machined workpiece is less. All right. So, therefore, the rubbing is less, temperature occurring is less, and the tool life increases. Now, after this point, when we have achieved the maximum tool life, all right, after that if you further increase the flank angle, exactly the same thing happens as in case of the rake angle, that the tool life falls, and the tool life falls because with further increase in the flank angle, as I have shown it to you, that the tool cutting angle is decreasing and the tool is becoming weaker, okay, and the less material is available for the heat conduction, and therefore, the afterwards it falls. After this point, if we further increase the flank angle, tool life falls. The rest of the material I will discuss in my next session of discussion. Thank you for your attention.